Well, hello and welcome to day 22 of Advent of Code. This was a particularly hard one for me. It took me multiple days to write a solution to it. So the first part is quite straightforward, and I think most people wouldn't have had many problems with it. The second half, however, you did have to think a bit about how you might solve it. Now, the way I ended up solving it was not a particularly efficient way of solving it. It probably took a couple of minutes to work out the answer. But after I had gotten the right answer, I checked out the Advent of Code subreddit, and there were some amazing solutions there that would run in split seconds. And so if you're looking for an efficient solution, I can highly recommend you check out the solutions thread on the subreddit. However, the way I solved it, I thought was kind of interesting. I ended up, I can't really visualize or I find it really hard to imagine things in 3 dimensions. But 2 dimensions are relatively easier to reason about. And so the way I approached the second half of this is that I wrote a solution in 2 dimensions, and then I extended my algorithm, all my data types from 2 dimensions to 3 dimensions, and reran it on the full data. And that worked. And I think that's an approach to solving mathematical things I kind of picked up from watching the wonderful YouTube channel, Three Brown, One Blue, Three Blue, One Brown, Three Blue, One Brown. Let me get that right. Where he always suggests that when you're solving a complex mathematical problem, start with something that's easier. In this case, for me, that's starting with 2 dimensions. And then once you've gotten a solution, then extend it to the harder ones. And that really helped me with this one. So although my solution was not a particularly efficient one, I thought it was kind of interesting. So I'd like to share that with you in this video. So the first part, I'm not really going to go into it in too much detail. It's quite straightforward. The input looks something like this. And for the first part, you only have to worry about the first set of numbers. And you can do this the naive way, right? Where you simply parse each instruction as it comes in. I don't think this was actually necessary, but I just didn't want to go through and check the data. I'm just making sure that x1 is always less than x2, and so my loops here will always work. And then, yeah, if it was on, you pop it into a map, and if it's off, then you delete it from the map, and then in the end, you just count the number of items you have in the map, and these are all the points in your input, and you get the answer, and it runs quickly. The only thing to watch out for is that these loops are less than or equal to, because the problem specified that these bounds are inclusive. So this is 10 to 12 inclusive. This is a length 3, not length 2. And so you just had to be a little bit careful with your comparison signs. But apart from that, it was straightforward. And of course, I think anyone who did it this way would have tried to run it on the full data set and immediately run into a problem where the inputs are way too big to be able to process it this way. Now, maybe you could have left this running overnight, I don't know, but we want something a bit more efficient than this. And so the solution I came up with, which was not the most efficient, but it was to keep track of regions that are on instead of individual points that are on. So what do I mean by that? Well, let's say you have 2 overlapping regions like this that both need to be on. We want to be able to count this using just area, right? We're thinking in 2 dimensions for now. So in terms of area, we want to take the area of this rectangle, and then we want to take the area of this rectangle, but we don't want to double count this one here. And so what I did was I took, for every overlapping rectangle, I would take all the overlapping points, as you can see here, carve it up in 2 dimensions, carving it up into all the individual rectangles that would make up the shape, and then checking each individual rectangle whether or not it was within the bounds of the areas that we cared about, and then yeah, keeping those rectangles. And what this means is that in the end, I can just sum up the areas of all the rectangles I have, and that would be that. So in terms of code, I have a lot of test data because it took me a lot of time to do this. So what I did was I created a couple of helper types. First thing is this rectangle type. For rectangle type, for me, I prefer using the coordinates. Some people prefer X, Y, and width and height. It's the same thing, it just means you have to do different kinds of calculations in different places. And so I just define a couple of helper functions for that. So in this case, getting the area of the rectangle, that's a straightforward algorithm. Made this int64 because as you can see, once you get to the end, the numbers can get pretty big, and I just didn't want to run into any overflow issues. I had an in helper function, and in tells you whether or not a rectangle is within the bounds of the other rectangle, so whether this rectangle is within this rectangle, and I defined within as being inclusive of the bounds, as you can see from my greater than and less than signs. And that's just particularly helpful because like this rectangle here, for example, clearly overlaps with this rectangle here. And I still wanted that test to be true. So that should hopefully be quite straightforward. This intersects algorithm I found online. I'm not particularly good with my spatial algorithms. So this doesn't actually just test for intersection, but this will actually give you, if you took these coordinates, it would give you the actual intersecting rectangle. And I needed that. No, I didn't need that. So maybe there's a simpler algorithm, but I found this was the first one I found and it worked, so I just kept it. If this is true, these are the actual corners of the intersecting rectangle. So those are my helper functions for my rectangles. And then I just define a type called plane, which is just an array or slice of rectangles. And so my algorithm is basically take each line from my input. In this case, I just have one input for now. And as you can see, we process that instruction, 1 of 1. We have a rectangle from 0 to 5, and then an area of 25. So you'll see the first discrepancy you'll see here is that this is 0, 5, and this is 0 to 4. Remember that the input is inclusive of its bounds, but a lot of these algorithms work much better if the top left bound is inclusive and the bottom right bound is exclusive. And so at some point, I simply add 1 to all the, you can see here, I just add 1 to all the other bounds. And all of the maths works out so much nicer if you do this. I think that was one of the observations of this, right? Because if you think 0 to 4 inclusive, that's 0, 1, 2, 3, 4. That's a 5 by 5 rectangle. So that's how I stored it. And yeah, we're only working in 2 dimensions for now, but I didn't want to change my, I wanted to be able to parse the actual input just to have a bit more test data. And so I just ignored the Z for now. So my way of testing for this is first, I make a list of all the intersecting points. So that's finding all the x points. So that's this x value here, and then this x value here, and then this x value here, and eventually this x value here as well. So it's 4 x values. Do the same with the y's, and that means I can get this grid, which basically, let's see. Yeah, so that's getting the grid. But before we get the grid, first we want to test whether or not rectangles intersect. And so for each new rectangle that we're processing, we're going to check it against the list. Pointer P is my plane. This gets a little bit hard to read because I have to put all these brackets around pointer P. But, so just try and overlook that. I basically test for every new rectangle in my list, I check it against all my existing rectangles, whether or not this rectangle intersects with those. And if it does, we simply, we delete the intersecting rectangles out of our collection of rectangles so far, and we add it to this intersects slice that we just keep track of for now. Now what I do here is I do the sort and unique, and so there are just a whole bunch of edge cases with the way that rectangles overlap. For example, if they have the same x and y coordinates, for example, if they overlapped like this, let's say, then you might need to do something a little bit different. I hope this makes sense when you see this sort of diagram. If they overlap like this, then suddenly you don't have as many rectangles to create. And so that's just how I did it. I sorted them. I sorted all my x coordinates, all my y coordinates uniquely and unique them. And so I just have this list of, so for example, in this particular case, my x's here will be, my x's here, sorry, will be this, this x value, and this x value, then this x value, and then this x value, and the same for my y's, right? It would be this y, and then this y, and then this y, and then this y. And what that lets me do is it lets me construct all 9 of these rectangles. So just looping through that list of x's and y's and creating every single one of those rectangles. For each rectangle, we'll skip down to here. We're going to check if it's in either one of the existing rectangles. And so this is just a long way to write a exists function in Go. And basically what I'm doing is, out of those 9 rectangles, we'll see that these 7 highlighted rectangles are within the bounds of those 2 incoming rectangles. And so those are the 7 rectangles that we keep. Now that's for the case where the second rectangle is on. Now for the case where the second rectangle is off, we do the same thing. That's just here. But if it's in the off rectangle, then we just don't add it back into the list of rectangles that we're keeping track of, right? And so hopefully that makes sense. So we do the same thing, but this time we'll find that only these 3 rectangles are within and on. And so those are the 3 that we keep. So hopefully that makes sense. So that's how I decided to do this. What you'll soon realize though, is that if you do this, so here's the case of 2 intersecting on rectangles. Yeah, let's start with the off, actually. So we'll do this off case, and this is the case in my kind of ASCII diagram. You'll see we end up with 3 rectangles in the end. And the bounds, if you do take your time to kind of process what these bounds are, this is 1 coordinate, top left coordinate, and this is bottom right coordinate. You'll see that they represent these 3 rectangles here. And so there's that. And then if we had 2 on rectangles, we'll end up with the first case that we looked at. And then here you'll see that there should be 7 rectangles left over. And indeed, there are 7, 1, 2, 3, 4, 5, 6, 7 rectangles left over, and whatever that count is supposed to be, because we just take the area and sum them all up. So that works pretty well. It works out okay for a 2D case. And in fact, let's see. Oh, I did have a 3-way case. So the way, I'm not going to go into this, but the way my algorithm works is it finds every intersecting rectangle and it does them all. So in this case, with 3 rectangles, we end up with a whole bunch of rectangles down here. I believe the count is 18, but yeah. So if we did this two-way case on some input data, let's say test 1. Actually, no, we'll do it on the actual test data. Do I have the actual test data here? I don't. Okay, never mind. So let's do this on test 1, for example, which is a bigger list. You'll see we end up with, let's see, what do we end up with? 522 rectangles and whatever that area is supposed to be. And this is okay. This works. So what I did from this point on was I actually converted this to 3D. So to convert this from 3D, it's actually not as hard as it looks. We just have to go through each of these and systematically change the functions to work with 3 dimensions instead of 2. So first thing is that instead of rectangles, we're going to have cuboids, but I'm going to use cube because it's a bit shorter. I can't rename them. Okay. I'm just going to actually go through and check them like this. Cool. This is no longer a plane. I don't know what a three-dimensional plane is. Apparently it's called a hyperplane, but that's really long. So I decided to use the word space. Don't know if that makes sense, but let's pretend it does. So first thing is, of course, we have Z1, Z2. This is no longer the area, but this is the volume. And to work out the volume, of course, you just extend it into 3 dimensions. Z2 minus dot Z1. And I think this was the interesting part of the problem for me, was that you didn't really have to fully be able to visualize how these algorithms worked in 3D space. You just had to extend the 2-dimensional version logically, and it would work in 3D. And by the same virtue of that, if this happened to be a 4-dimensional problem, I'm sure you could apply the same logic and just add a 4th dimension to this the same way. Now, humans definitely can't reason in 4 dimensions. We just don't have that intuition. But you could do the same thing and it would still work. And I think that was kind of a little bit of that beauty behind doing it this way. Again, if is something in another one, I just have to look at my previous thing, extend it, and just change it to from Y's to Z's. And I could kind of trust that that would do the right thing. Now, intersects was a little bit trickier. This actually did trip me up a little bit, and it turns out this was the one that was a little bit tricky. You'll see that here, the extension, you would think the extension is to just go and Z, in this case, I renamed it to Zmin is less than Zmax. Actually, that's not the correct algorithm. The correct algorithm is actually to check each of these. Now I had an intuition. I don't know if this is actually correct or if this is the best way to write it, but I had the intuition that this was right, and I don't know how I had that intuition that this was the right way to extend it. But I did it and it worked. So if anyone knows, I appreciate learning why this is correct. But this is the correct extension of the intersects function. And so from this point on, this is not actual x. This works on a 1-dimensional slice, so we can ignore that. We're going to get to this compact algorithm later. And then, yes, the main one, right, which was extending this exact function, the core of the logic, into 3 dimensions. But we go through and we do the same thing, right? We check if Z2 is less than Z1, we swap them around, and I don't think this was necessary. I still don't think it's necessary. Here we need x, y, z1, x2 plus 1, z2 plus 1, in which case I do realize I made a mistake earlier. This is not meant to be in this order. Z1 is supposed to go here and Z2 is supposed to go there. Well done if you caught that when I was typing it. So here we just extend it. We need some Z's as well. And I'm doing this semi-blindly. I'm not really thinking about it too much. Which is kind of my whole point, that you can do this blindly. So every time I see Z's, X's, and Y's, I just add a Z's to it and do the same thing. So here, clearly we need another loop, this time looping over z's. We need to build a new rectangle, so z's, let's just chuck it in there. This seems to be fine. This seems to be fine. This seems to be fine. So theoretically, that is going to give me my 3D rectangle. So let's just see how that works. What we're going to do is we're going to take the first 2 inputs from here and see what happens. Just going to fix some, all right, missing a close parens there. Let's just do 1 input and make sure that that is okay. And then we can reason a little bit about 2 inputs. We look at this and we say, okay, we add 1 rectangle. It looks like the bounds are correct, right? Minus 20, minus 36, minus 47, which is our top left corner or top left up corner. Then 27, remember it's plus 1, 17, 18, and 8, so bottom right corner. And kind of the beauty of it was, I keep talking about this, I've added a dimension, and it's right. And it seems like I'm getting some sort of sliced up version of this rectangle. We can see that the x1 overlaps, and so we're not getting the 27 cuboids that we're expecting. We're getting a bit less than that, but it should be okay. And the way we can kind of test whether this works is we just pop in some of this test data that they give us. So just going to pop that in here. We'll start with the first one. So we should turn on 27 cubes, it says, and we've turned on 27 cubes. The second step, we turn on an additional 19 cubes. 19 plus 27 is 46, I believe. So we just check, does that say 46? It says 46, so that seems okay so far. The third step turns off 8 cubes, so we should be at 38 if we process the third one. And we are at 38. And we turn on a single cube at the end to get to 39, and we get 39. So that seems to be okay. So we just run it on a bunch more test data. For example, here we'll run it on, let's say, my original input to see if this works for the first part of the for part 1, to see if this new algorithm still works for part 1. Right, I don't actually have data in here, apparently. Just gonna grab that. Just make sure I have data in here. Cool, so the first 20 inputs is for my original input. Here we go. So it runs it on the first 20 rows things, and we see the answer is the correct answer, which is great. But you'll notice one thing is that this ran a lot slower than the naive solution. But this is meant to work better for the big cases, right? Now, on some level, it is actually faster because we can actually get past the 20th thing. Remember, with the naive solution, I couldn't get past the easy stuff. Whereas with the non-naive solution, we do actually get past we can get into like the 60-something line, but at some point, it just slows right down because what we're doing is we're generating all these small cubes or cuboids, and they get smaller and smaller and smaller because we're chopping them up to the point where they're so small that we're basically back to the naive solution already. So we're getting further, but we're not getting far enough. So what I decided at this point to do was that I needed another step. And the step I needed was this idea of compacting my rectangles. So it's not enough to just get to this part because we have all these rectangles that are being generated. I needed to somehow turn them back into giant, bigger rectangles, bigger swaths of rectangles. In fact, this is wrong, right? Because these are supposed to be like this, if we were to draw this diagram correctly. And I guess these aren't pluses, but whatever. And this is what we want. And so I did the same thing that I did before. And what we're going to do is we're going to run this on a different file again. So this file has both the 2D and the 3D versions combined together. I wrote this algorithm called compact. And in 2 dimensions, what we do is it's a little bit cryptic. And it's probably not the best way to do it, but it's the way that I ended up doing it. First, I sort my rectangles so that all the ones with the same y directions are right next to each other. So I'm just putting one. The result of this sort, it's a little hard to explain, and for me to explain. It's not that hard to understand, but I'm sorting all the rectangles that can be compacted so that they end up next to each other in my slice. And because they're next to each other in my slice, all I'm doing here is processing the ith rectangle with the I minus 1th rectangle. I'm going through it backwards because I'm doing some deleting as I combine them together. And so I sort them so that ones that can be merged are right next to each other, merged in the x direction are right next to each other. And then I just go through, if they're mergeable, I merge them into a bigger rectangle and I delete one of them. So I end up with one fewer rectangle. And then I sort them again in the x direction, in the other direction, whichever one I haven't said yet. And I do the same thing and I merge them in the other direction. So here I have a print line that says how many rectangles I started with and how many I ended up with. You'll see here in this example, for example, we have 7 rectangles that can be merged into 3. And if I ran a test, not this, but let's say with this test data here, we do this for the 2-dimensional case. I compact them you'll see here that it had originally those 7 rectangles that we compacted into 3. And if you do parse out these coordinates, you will find that they turn from this case into exactly this case. And so that way, because I end up with fewer rectangles, which are bigger, again, this is less processing for the computer. And that's the idea behind that compact algorithm. And here's a better example where I have 3 rectangles, 2 rectangles that don't overlap, and then a third one that overlaps with both. Now, originally, this would have generated, I think, 18 rectangles. But after compacting it, I ended up with 5. And so again, we do the same thing, right? The compact algorithm, where is it? Does this on 2 dimensions. So to extend it into 3 dimensions, I do the same thing. I just have to make sure my sort algorithm is correct. I sort to have the same x's and y's next to each other. And then I just check if 2 cuboids have the same x and y coordinates and the y and z coordinates and the x coordinates line up the right way, then I can merge them into one big cube or cuboid. And then I do the same thing and I check when the x's and the z's line up, and then I merge along the y axis dimension, and then I check that the x and y's are the same and I merge along the z dimension. I'm not really going to explain this any in more detail than this. But if I run this with the compact on my test, on my part 1 data, this is not my part 1 data for some reason. No, because I'm not doing this on a 2D, I need to do this in 3 dimensions. So I switch back over to my 3 dimensions, which calculates volume, not area. And now it does run relatively quickly. If I don't print out P and I just print out the length of P, the count of P, we get the same answer that I had for part 1. It runs a lot faster because it's doing that compaction is doing a lot of work, right? You'll see here, if we just go back through here, and you can already see it, we have 15 rectangles becoming 5, and then 68 cuboids becoming 9, 192 becoming 15, and so on. And at the end, instead of having hundreds of thousands of cuboids, we only have 67 cuboids, which is so much faster to process. But you will find that this is not actually as fast as it could be. And if I run it on my full data set, which I did, it still takes a couple of minutes. If you just pay attention to the number at the end of the compact, you'll see that actually at some point, these we are still accumulating cuboids. We still have more and more cuboids in the space, and it does take a couple of minutes to run all the way through my 420 cuboids. But I did sit here and let it run, and I got my answer. I put it in, and it worked out. So I think I'll just wrap this video up here. For me, I'm sorry if this kind of didn't quite make sense. I hope conceptually it made sense, even if it didn't give you the specific algorithms in order to solve it this way. But I just thought the concept of how I solved this was quite interesting, right? I solved, I wrote all my algorithms to work in 2 dimensions, and then I kind of just logically extended them to 3 dimensions, and that was good enough to solve this puzzle, even though it wasn't a particularly efficient algorithm in the end. You do see here we're accumulating quite a lot of cuboids. So this number here, by the way, is how many, this number here is how many cuboids we're generating at each point. We're generating more and more cuboids at each point because every intersected cuboid creates all these additional cuboids to check. But yeah, it was just fascinating to me to see how we could take a 2-dimensional algorithm and extend it to 3. If you're looking for an efficient solution, like I said at the beginning, check out the subreddit, the Advent of Code subreddit, because there are some amazing solutions there. But that's it for this, for my solution to day 22. I'll probably put up my untidied up code in a gist, just so you could take a look at it in a bit more detail if you're interested. But I'm sorry that I'm not going to let this run all the way to the end. It will just be a video sitting here that's quite long. For me, this was probably this year's hardest challenge. I have, at this point in time, I have actually solved all the other puzzles already. But yeah, it was fun. It was fascinating of how you could extend it. And yeah, I hope you found that interesting too. So thank you for watching, and I'll see you again next time.